When I talk about the fate of the universe, I am not talking about a story with a moral lesson. I'm talking about a physical system that follows rules. Those rules are gravity, quantum mechanics, relativity, and thermodynamics. Our systems measure how the universe behaves, write down the laws that fit those measurements, and then ask what those same laws predict for the far future. The picture that emerges is powerful, but it is not complete. We know some key numbers very well. We also know that some of the most important ingredients, like dark matter and dark energy, are still mysterious in their nature. So I will walk through what we think the universe is made of, how it is evolving, how we know, and what that implies for its ultimate fate. I start with expansion. In the 1920s, Edwin Hubble and others measured distances to galaxies using standard candles like Cepheid variable stars. They also measured how the light from those galaxies was shifted to the red end of the spectrum. Redshift means the wavelength of light has been stretched. They found that more distant galaxies had larger redshifts. The simplest interpretation within general relativity is that space itself is expanding. Galaxies are not flying through a pre-existing static space like bullets. Instead, the metric that defines distances between galaxies is changing with time. This is encoded in the Friedmann-Lemaitre-Robertson-Walker, or FLRW, solutions to Einstein's equations. In those solutions, the scale factor AT tells us how distances grow or shrink with cosmic time. The Hubble parameter HT is the rate of change of that scale factor divided by the scale factor itself. Today we measure Hubble's constant, H0, to be on the order of 70 kilometers per second per megaparsec, with some tension between different methods that I will come back to. The key point is that the universe is expanding. That is not speculation. It is directly observed in the redshift distance relation, in the cosmic microwave background, and in the distribution of galaxies. If the universe is expanding now, we can ask, was it smaller in the past and will it expand forever in the future? General relativity gives us a way to connect the expansion rate to the contents of the universe. In the Friedmann equations, the curvature and time evolution of the scale factor are determined by the energy density and pressure of everything that exists: radiation, matter, dark energy, and any other fields. Different components dilute differently as the universe expands. Radiation thins out as 1 over AT to the fourth power because photons get farther apart, and each photon also loses energy due to redshift. Matter, which includes normal matter and dark matter, dilutes as 1 over AT cubed because the number of particles per volume goes down as space expands. A cosmological constant, which is one possible form of dark energy, does not dilute at all. Its energy density stays constant even as space grows. We infer the composition of the universe from several independent measurements. The first is the cosmic microwave background, or CMB. This is relic radiation from when the universe was about 380,000 years old and had cooled enough for electrons and protons to combine into neutral hydrogen. Before that, the universe was a hot plasma that scattered photons efficiently. After recombination, photons could travel freely. We see them today as a nearly uniform background at about 2.7 Kelvin. Tiny temperature fluctuations in the CMB at the level of 1 part in 100,000 encode information about the density, composition, and geometry of the early universe. Satellites like COBE, WMAP, and Planck have mapped these fluctuations across the sky with high precision. When we fit theoretical models to the power spectrum of these fluctuations, we find that the universe is spatially very close to flat on large scales, and that its energy budget today is roughly 5% normal matter, about 25% dark matter, and about 70% dark energy. Dark matter is called dark because it does not emit, absorb, or scatter light in any significant way. We detect it through its gravitational effects. The classic evidence comes from galaxy rotation curves. In the 1970s, Vera Rubin and others measured how fast stars orbit in the outer regions of spiral galaxies. If only visible matter were present, the orbital speed should drop with distance from the center, like planets in the solar system. Instead, the rotation curves stay flat. That implies there is extra mass in an extended halo around the galaxy. Similar evidence comes from gravitational lensing, where mass bends light from background objects. Clusters of galaxies lens light more strongly than visible matter alone can explain. The pattern of large-scale structure, how galaxies cluster in three-dimensional surveys, also requires an additional, non-relativistic matter component to grow structure at the observed rate. All of this is consistent with cold dark matter, a population of particles that move slowly compared to the speed of light, interact weakly with normal matter, and contribute only gravitationally on large scales. Dark energy is more subtle. In the late 1990s, two teams used Type 1a supernova as standardizable candles to measure distances to faraway galaxies. A Type 1a supernova has a characteristic peak luminosity because it comes from a white dwarf in a binary system reaching a critical mass and undergoing a thermonuclear runaway. By comparing the observed brightness to the expected intrinsic brightness, we can infer distance. Combining that with redshift measurements gives us the expansion history. The teams expected to find that the expansion of the universe was slowing down under the pull of gravity. Instead, they found that distant supernovae were dimmer than expected. That means they were farther away than a decelerating universe would place them. The simplest explanation is that the expansion of the universe has been speeding up for the last few billion years. We call that accelerated expansion dark energy. In general relativity, energy and pressure both gravitate. A component with negative pressure can cause accelerated expansion. A cosmological constant, lambda, has an equation of state parameter W equal to -1, meaning its pressure is negative and equal in magnitude to its energy density. Plugging that into the Friedmann equations, we find that a positive cosmological constant leads to acceleration. Observations of supernovae, the CMB, and baryon acoustic oscillations in the galaxy distribution are all consistent with a dark energy component whose W is very close to -1 and whose density is about 70% of the critical density today. Whether dark energy is exactly a cosmological constant, or a slowly evolving field, or something more exotic is still unknown. But its effect on the expansion is measured. Now, the fate of the universe depends crucially on the relative amounts of matter, radiation, and dark energy, and on the equation of state of dark energy. In older cosmological models, before dark energy was established, we talked about three simple fates. If the density of matter and radiation was high enough, gravity would eventually halt the expansion and reverse it. The universe would recollapse in a big crunch. If the density was exactly at the critical value for a flat universe, expansion would slow but never quite stop, leading to a critical or marginally bound universe. If the density was below critical, the universe would expand forever with a positive curvature of spacetime, an open universe. With dark energy in the mix, this simple classification changes. Even a flat universe, like ours appears to be, can accelerate and expand forever if dark energy dominates and does not vanish. To see why, I think in terms of the scale factor AT. Early on, radiation dominated. As the universe expanded and cooled, matter took over. During radiation domination, AT grew roughly as T to the 1/2 power. During matter domination, AT grew as T to the 2/3 power. Both are decelerating expansions. Once dark energy becomes dominant, if it is a cosmological constant, the expansion approaches exponential growth. The scale factor grows like e to the power of HLT, where HL is roughly constant. That means that in the far future, distances between unbound objects will grow faster and faster. Gravity can still hold together structures that are already gravitationally bound, like galaxies and galaxy clusters, but regions that are not bound will be pushed apart more and more quickly. The Hubble radius, which is roughly the distance at which the recession speed equals the speed of light, approaches a constant in a pure cosmological constant universe. Objects beyond a certain distance will eventually recede from us faster than light due to the expansion of space, and their light will never reach us. A common question is whether faster than light recession violates relativity. It does not. Special relativity limits how fast objects can move through local spacetime. It does not limit how fast the metric itself can change. In general relativity, distant galaxies are not moving through space faster than light. Instead, the space between us and them is stretching. Light emitted from them may be carried away by the expansion and never cross the horizon to reach us. This leads to the idea of a cosmic event horizon in an accelerating universe. There is a finite region of space-time from which light signals can ever reach us, even if we wait forever. As dark energy dominates more completely, that horizon size tends toward a constant value on the order of tens of billions of light years in comoving coordinates, depending on the exact parameters. So, in the current standard model of cosmology, called lambda cold dark matter, or LCDM, the best fit parameters suggest that the universe is spatially flat on large scales, dominated by a cosmological constant, like dark energy, with cold dark matter and normal matter making up the rest. In that model, the fate of the universe is eternal accelerated expansion. There is no recollapse. There is no global turnaround. Instead, structure formation gradually shuts down. Gravity has already pulled matter into galaxies, groups, and clusters. Over tens of billions of years, galaxies within bound structures will merge into larger elliptical galaxies. Within our local group, the Milky Way and Andromeda will merge in about 4 to 5 billion years, forming a single large galaxy. The local group itself is gravitationally bound and will remain intact. But more distant galaxies, not gravitationally bound to us, will continue to recede. Over trillions of years, almost all galaxies beyond our local group will cross our event horizon. Their light will be redshifted to such long wavelengths that they become undetectable. To far future observers in our merged galaxy, the universe will appear dark and empty beyond their local structure. The evidence for expansion and the Big Bang will be much harder to infer. On even longer timescales, stars burn their nuclear fuel. Low-mass stars, like red dwarfs, can live for trillions of years, much longer than the current age of the universe. But eventually, even they exhaust their hydrogen. The universe enters what is sometimes called the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes, along with cold gas and dust. Proton decay, if it happens, would further erode matter over timescales of at least 10 to 34 years, according to some grand unified theories. But proton decay has not been observed, and current experimental limits push the proton lifetime beyond 1034 years. So we do not know if ordinary matter is ultimately stable. Black holes slowly lose mass via Hawking radiation, a quantum effect in curved space-time, where particle-antiparticle pairs near the event horizon lead to a net loss of mass. A stellar mass black hole takes around 1067 years to evaporate. Supermassive black holes, like those in galaxy centers, can take up to 10 to 100 years or more. After that, the universe in the LCDM picture would be a very dilute bath of low-energy photons, neutrinos, and possibly some long-lived particles, expanding exponentially due to dark energy. This long-term scenario is sometimes called heat death, or the big freeze. It is not a sudden event. It is a gradual approach to a state in which free energy, the kind of energy that can do work and drive structure formation, is mostly exhausted on large scales. Thermodynamically, entropy increases and the universe becomes more uniform at the largest scales again, but now at extremely low temperature. The cosmic microwave background, which is already at 2.7 Kelvin, will be redshifted to much longer wavelengths and lower temperatures. The characteristic temperature of the de Sitter horizon associated with a cosmological constant is small but non-zero, so there is a residual thermal radiation tied to the horizon. However, these details are deep in the regime where quantum gravity and horizon thermodynamics intersect, and our understanding is incomplete. This is one possible fate, based on the assumption that dark energy is exactly a cosmological constant and that the laws of physics we know today remain valid for arbitrarily long times. But we have to be honest about the uncertainties. One major uncertainty is the nature of dark energy. We parameterize it with W, the ratio of pressure to energy density. For a cosmological constant, W equals -1 exactly. Observations so far are consistent with W being very close to -1 within a few percent. But they do not absolutely rule out small deviations or slow evolution of W with time. If W is slightly greater than -1, say -0.9, dark energy would still cause acceleration, but its density would dilute slowly as the universe expands. In that case, matter could eventually redominate and the expansion might change behavior. If W is less than -1, we call that phantom energy. In such models, the energy density of dark energy actually increases with time as the universe expands. That leads to a very different fate, a big rip. In a big rip scenario, the scale factor diverges in a finite proper time. The expansion rate accelerates so strongly that first galaxy clusters, then galaxies, then solar systems, and finally even atoms are torn apart as the repulsive effect of dark energy overwhelms all binding forces. We can calculate the time remaining until the big rip from the value of W, if W is constant and less than -1. Observations currently do not favor such extreme phantom behavior, but they do not completely exclude W slightly below -1. The challenge is that measuring W precisely and tracking any time variation requires very accurate distance and structure measurements over a wide range of redshifts. Projects like the Dark Energy Survey, the Euclid mission, and the Nancy Grace Roman Space Telescope are designed to improve those constraints. Until we know and its evolution more precisely, we cannot fully rule out alternative fates. Another uncertainty lies in the Hubble constant tension. Different methods of measuring H0 give slightly different values. Local measurements, which use Cepheids and type Ia supernovae anchored to nearby distances, tend to give a higher H0, around 73 kilometers per second per megaparsec. Early universe measurements, which infer H0 by fitting the CMB power spectrum within LCDM, give a lower value, around 67. This discrepancy is statistically significant and has not yet been fully explained. It could be due to subtle systematic errors in one or both methods. Or it could hint at new physics beyond the standard LCDM model, such as early dark energy, extra-relativistic species, or other modifications. If the underlying cosmology is slightly different from LCDM, that could alter the inferred composition and thus the far future behavior. Right now, LCDM with a cosmological constant still fits a wide range of data remarkably well, but we have to keep testing it. We also do not know what dark matter is at the particle level. Many candidates have been proposed. Weakly interacting massive particles, axions, sterile neutrinos, and others. Direct detection experiments like underground detectors searching for rare scattering events and collider experiments like those at the Large Hadron Collider have not yet found a conclusive signal. Astrophysical observations tightly constrain how dark matter clusters and how cold or warm it can be. But the microphysics remains unknown. For the fate of the universe on the largest scales, the detailed nature of dark matter is less critical than its overall abundance and its gravitational behavior. However, if dark matter has self-interactions, decays over long timescales, or couples in some way to dark energy, that could change the long-term evolution. Most models assume dark matter is stable on cosmological timescales and interacts only gravitationally, which leads back to the LCDM fate. Another line of thought involves modifications of gravity itself. General relativity has passed many tests in the solar system, in binary pulsars, and with gravitational waves. On cosmological scales, though, we mostly infer gravity's behavior indirectly by fitting models to large-scale structure and expansion data. Some theorists propose that what we call dark energy might instead be a sign that general relativity needs modification on large scales. Examples include FR, gravity, scalar tensor theories, and massive gravity. These models can mimic a cosmological constant for some period, but then deviate in the far future. In some cases, the acceleration could be a transient phase, followed by a return to decelerated expansion or even recollapse. Observationally, we can test modified gravity by looking at how structure grows over time, not just how the universe expands. Dark energy that is a smooth cosmological constant affects expansion but not the clustering of matter directly, while modified gravity often leaves signatures in both. Current data are consistent with general relativity plus dark energy, but the error bars still leave room for alternatives. Even within standard general relativity, quantum effects might become important for the fate of the universe. The cosmological constant problem is a major open issue. Quantum field theory predicts a vacuum energy density that is many orders of magnitude larger than the dark energy density we observe. Somehow, the effective cosmological constant is extremely small but non-zero. We do not know why. Some approaches to quantum gravity, like string theory, suggest that there might be many possible vacuum states with different values of the cosmological constant. Transitions between these states could, in principle, change the effective dark energy in the future. For example, a metastable vacuum could decay to a lower energy vacuum, releasing energy and changing the expansion behavior. This kind of vacuum decay is a quantum tunneling process. If it happened, it would create a bubble of the new vacuum that expands at nearly the speed of light, altering the laws of physics inside. However, we have no direct evidence that such a decay is likely on any relevant timescale, and our ability to calculate the lifetime of our vacuum is limited. From an observational standpoint, we treat dark energy as constant until data show otherwise. When we talk about the fate of the universe, we also have to consider the role of horizons and information. In a de Sitter-like universe dominated by a cosmological constant, there is a cosmological event horizon with an associated entropy and temperature. This is analogous, in some ways, to a black hole horizon. The horizon entropy scales with the area of the horizon in Planck units. As the universe expands and approaches de Sitter space, the total accessible entropy is finite. Black holes within this space also have entropy. The interplay between black hole evaporation, horizon thermodynamics, and the overall arrow of time is an active research area. We do not yet have a complete theory that unifies quantum mechanics, gravity, and cosmological horizons. This means that our description of the very far future, when only horizons and long wavelength radiation remain, is incomplete at a fundamental level. Let me connect this back to how we know what we know. The key observables are the Hubble diagram of supernovae, the anisotropies of the cosmic microwave background, the three-dimensional clustering of galaxies, the weak gravitational lensing of background galaxies, and the abundance and evolution of galaxy clusters. Each of these probes different combinations of parameters: the matter density, the dark energy density, the equation of state, the curvature, and the amplitude of primordial fluctuations. By combining them, we can break degeneracies and test consistency. For example, the CMB tells us about the early universe and sets initial conditions. Large-scale structure tells us how those initial conditions evolved under gravity. If the same set of parameters fits both, that supports the model. So far, LCDM does this remarkably well, but small tensions like the H0 discrepancy and some mild differences in structure growth amplitude keep us cautious. We also use standard rulers like baryon acoustic oscillations, which are imprints of sound waves in the early universe's plasma, frozen into the distribution of galaxies. The characteristic scale of these oscillations provides a known length that we can observe at different redshifts. That gives us a way to trace how distances scale with redshift, which is directly tied to the expansion history. Weak lensing, the slight distortion of galaxy shapes by intervening mass, tells us about the matter distribution and how it grows. Cluster counts as a function of redshift tell us how structure formation proceeds in different cosmologies. All these measurements converge on a universe where dark energy has been dominant only in the last few billion years, and where its influence is growing. On human timescales, the fate of the universe is not something we will see unfold. The accelerated expansion is gentle on the scale of galaxies and solar systems. Local dynamics are dominated by gravity within bound systems. The sun will exhaust its core hydrogen and evolve into a red giant in about 5 billion years, then shed its outer layers and end as a white dwarf. That is a dramatic event for our solar system, but cosmologically it is routine. The cosmic acceleration will have slightly altered the large-scale arrangement of galaxies by then, but local gravitationally bound structures will look much the same.